Hi, welcome to the ninth live session of PST2. Response to biology course in here. So today we'll first go with the first of assignment 3 solution already with this because in the answer some student has requested me to go through the assignments. So that's why today I'm going to the assignments, subjective and objective both assignment together I'm going. Okay. So first we shall go with the subjective assignment 3 and then we shall go with the objective assignment, right? Okay. So so let's start. One second. Okay, first question is the following. So this is nothing but assignment 3. Okay. First question. Show that closed subspace of a paracomplex space is paracomplex. Show that closed subspace paracomplex is paracomplex. Okay. So how to approach this problem? So so let X be a paracomplex space. Let A subset of X be closed. Now we need to show capital A is also paracomplex. So how to do it? So for this, what we will do? We will take some open cover of capital. So let's say U alpha Bn open cover of so let's say U alpha open cover of capital A. Okay. So this does what? This U alpha intersection is their complement. It is an solution, not obviously. It is an open cover of capital X, right? So since X is paracompact, so here exists a locally finite by definition this happens. So there is a locally finite open requirement E beta of E alpha intersection a complement. So this tells us what this is. Beta intersection capital A. This collection is an locally finite refinement of U1, right? So, this is the argument. Okay, so let me repeat the argument. So what we have done that X the parameter is given and let A be a capital A closed surface. Okay. Now I need to show its parameter not. So we will proceed by definition. So for that we choose an open cover U alpha of capital A. So U alpha intersection, U alpha union A complement is the open cover of capital A. Okay. Now X is given to a paracompact. So there exists a locally finite open refinement PB of U alpha union A complement. Sorry. So this implies what? V beta intersection A is a locally finite refinement of U. So this way this argument goes. Okay. There is really nothing much complication. It's only the simple application use, direct use of the definition. Okay. Okay. Wait. So the second question. So before going to second, let me give a definition because the definition is not. The definition is not applicable. Possibly is not in the class. So a split X be a space. Then X is said to be sigma compact. If it can be written as a countable union of compacts. So a space H2 is a compact, it can be written as countable as compact. That's okay. And it is called as sigma locally compact if it can be written as countable union of open sets closure compact. Okay. Now the question is that, so there are two to one is sigma compact or sigma locally compact. Sigma compact means it can be written countable compacts. Sigma locally compact means it can be written as countable unit open sets whose closure are compact. Okay. Now the question is that show that locally compact in the left space sigma locally compact. So this theorem tells us under which condition locally compact space with the sigma locally compact, because from definition it's quite obvious that sigma locally compact there is it need not be locally compact in general. Okay. On under linear condition this is so how to put it? So so for that what I do, so now sorry, so x is divided by locally compact. So for each x belongs to x, there exists an open set ux of that x belongs to ux and ux closure compact. Okay. Now by Lindelof-Ness condition, so Lindelof tells that there exists open source UI which covers it, and so x is equal to union I is equal to 1 to infinity ux closure and each x compact, which tells x is sigma locally compact. Okay, by the way, I have used the same notation as search themselves assignment solutions, because the reason is that so that the same notation will not create any type of confusion. Okay. Also, same notation is actually quite helpful for understanding at least two simultaneous at the same time. Okay, so Let me repeat the argument again. X is given to be locally compact and linear. Then you need to check that X is sigma locally compact. Okay. Since it's locally compact, so there's opens the UX such that X belongs to X. And linear still there is this then opens that UXI belongs to N and so the UX closure compact. This is given by locally compactness. Okay. So since this is the open curve, so X equal to union UI X UX closure is UI compact. This is the X is sigma locally compact. Okay. Okay. So this is basically direct application of the definition. Okay, there is nothing really much to say. Just you need to use the definition clearly, and there are some equivalent criteria for the same thing. We need to use that. So then it will be fine, to actually register problems. Okay. Also, do remember one thing: it's necessary to solve problem as much as possible because this type of things are quite abstract. Okay, so in order to get some idea, get feel for these problems, you need to solve. I mean, in order to clear these ideas, you need to um, solve problem as much as you can. Okay. So apart from this assignment, you can follow you can follow some books. One namely Dubunchi. Okay, so this is one book, Dubunchi. The assignment problems or those that book is quite interesting. Sorry, I mean the exercise is very interesting, and also you should solve this problems from different type of entrance examination. That will also be very much helpful. Okay. Okay. So let me start the next question. Just hold for 2 minutes. So the next problem is to give an open cover U, which is nothing but U alpha. Alpha belongs to J of a compact house of space H. Show that there exists a partition of unity theta alpha. Alpha belongs to J. Next by same set J. Does that support theta alpha subset of U alpha? So the question is that we have some U of U alpha which is open cover of some paracompact houseful space which is called X. Now I need to show that in such condition that it is paracompact, where we have a partition unit theta alpha indexed by the same set G. Okay. So the support phi alpha subset of U alpha. Okay. I mean, if you can remember the proof of existence of partition unity, and you can, and then if you, I mean, then if you modify this proof slightly, you will get this answer. Okay. So I mean, yeah, it's a very technical answer, but it's not difficult data. So let me discuss the answer for you. So the solution goes as follows. One second. So U is an given open covering of X, and X is given to the paracompact plus house top, right? So by the existence theorem partition unity, we will have a partition of unity I belongs to I, which is nothing but the subordinate to open cover U. Okay, and let we choose the function rho from I to j be refinement function, that is support of the theta is content of U of rho I. Okay, now we are defining theta alpha by taking sum over I such that Pi is equal to alpha. Now the claim is that this theta alpha forms a partition unity of X subordinate the cover Q, and it is not difficult, you can check it easily. If you have any doubt or confusion, you can ask me in the next session. I will clear it for you. And also this fact also, I mean, since it's a partition unity, so theta, this collection theta alpha is locally finite, right? But each theta alpha is summation of all those rows I, so that Pi is equal to alpha. So this implies this collection eta is locally finite, right? And so this tells that support of eta I is finite. It's locally, this collection is locally finite. And now observe that. Then so we need to check the support of theta alpha. Support of theta alpha is given to this union of, since it is theta alpha is summation eta I, so union of support those eta I, so that Pi is equal to alpha. Its closure. So union of support is equal to support is a closed set. Support of theta I says that Pi is equal to alpha. I mean, it's a closed subset G1. So support of is theta alpha. So support of is theta I, subset of U alpha. So this is what we are trying. This is the what the question asks us to show, right? So let me repeat the argument again. Let's hold it together. Let me find the next question that I will okay. So the problem is, so the argument is as follows. So the given property is capital X, paragon type and house shape. Okay, and we have some given open cover, and we need to find the partition unity over the same indexes are the support condition. Let's say the support of theta alpha substitute. Okay. So since the paracompact house structure, so we already exist a partition unity call it theta I, which is subordinate to the given open cover U. Okay, and let rho I to j be some refined function that is support theta such that U rho I. Okay. Now we are defining theta alpha to be all sum of all theta I such that rho I is equal to alpha. Okay. Now the claim is that this theta alpha, this collection theta alpha forms and partition unit subordinate to U, and theta alpha is locally finite. Okay, so this is clear. I mean, it's not difficult to prove. Now since theta alpha is equal to summation of eta I, so is eta I. I mean, so the collection eta is locally finite, and so support of eta is locally finite. This collection now support of support of theta alpha is equal to union of support of eta I, so that rho I is equal to alpha, its closure. And it is shown that it is contained inside U alpha. So support of theta alpha subset of U alpha. This is what we need to show. So this is the full argument. Okay. Well, the thing is that you might think this argument is not quite natural. Yeah, you are right. This is not something naturally come. So that's why it's always better to solve different problems so that you can understand the concept and you can understand how to apply the theorems under in which situations. Okay, I mean solving the problem makes you mature regarding a particular concept. Okay, that's why practicing something is extremely important. So the next question is the fourth. So that sigma locally compact is locally compact if and only if it is sigma compact space. Okay. So sigma locally compact is compact if and only if the sigma compact space and locally compact. Okay. So how to approach this problem? So it is given the space is sigma locally compact, and if the space is sigma compact and locally compact, sorry, if, okay, sigma locally compact if and only if and only sigma it is sigma compact and locally compact. How to do it? So what are the information here? Sigma is locally compact, that is for each open set we will have a neighborhood which can, sorry, for each locally compact means each point x we will have a neighborhood whose closure is compact. Okay. And sigma compact means what? Can be written as countable union of compact. But sigma locally compact is what? It can be written as countable union of open set whose closure is compact, right? So how to use these things together? Okay. So try to do it by going to definition. I should have the sentence. Okay, so so the argument goes as follows. So first we're going to solve the if part. Okay, let X be sigma compact. Then there exists an increasing sequence of compact sets K n dash shares that union of K n dash equal to X. Okay. Now by local compactness, for each X belongs to X, there exists an operator Ux such that X belongs to Ux and Ux closure is compact. Now what we wish to do, we wish to construct a collection of open sets inductively such that closure of that open set is compact, and each of this open set, if we index it by v1 with vn, each of the open set vn contains the set kn dash. Okay, we are going to construct such vns inductively. Okay, so take v0 is equal to phi. Okay, so the question is how to get v1 from v0. Okay, so assume we have constructed vn minus 1. Assume this. Now since Kn dash union being closure immanent or compact, so there is x1, x2, xr such that Kn prime union v closure in minus 1 is subset of ux1 subset of uxr is equal to Pn. Okay, and this tells that Pn closure is equal to ux1 closure dot 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 uxl closure. It's compact. And Kn dash subset of Pn. It follows that union, it follows the x as well union in. Okay, so this is what we have done for the first part. That is, we have assumed that the space is sigma compact as well as locally compact, and then by some process we have shown that it is sigma locally compact. Okay, so before going to the reverse direction, let me repeat this argument. I think it's better because this argument is quite clever argument. Okay, so one second. So so since X is sigma compact, so we will get a sequence of compacts at Kn such that union Kn dash is equal to capital X. Okay, it is by sigma compactness. And by local compactness for each x belongs to x, there is an open set ux such that x belongs to ux and a ux closure compact. Okay. Now, uh, the main technique is that um, we are going to constants of Vn such that each of the open set Vn contain the set k dash n for each n. Okay. Now the construction will be carried out by inductive method. Okay. So first we take V0 to be empty. Now the question is how to get V1 from V0. So since we are going to construct inductive, let's assume that Vn minus 1 has already been constructed. Now let's see how to get Vn from Vn minus 1. Now observe that Kn dash union Vn minus 1 closure is compact. Okay. So we will get some final points, economistic thoughts, other Kn dash union. Kn dash union Vn minus 1 close after ux1 dot dot uxr. Call this ux1 dot uxr to be Vn. Okay. Now the closure distributes over union, so Vn closure equal to u x1 closure dot dot uxr closure, which is compact, and K index is a subset of Vn. So this tells that X is subset of union. So sigma compact plus locally compact equals sigma locally compact. Okay. So now we can understand why the sigma locally compact word. How and why this word sigma locally compact coming. Okay. So now let's go to only if one. Okay. That is assume that X is sigma locally compact. Okay. We need to check X is locally compact, and we also need to check X is sigma compact. So we are taking some open cover UN. For each UN open and UN closure compact, this is what we're getting as definition of compact, sigma locally compactness. Okay. So obviously this tells this thing tells that X is sigma compact. Right. Now how to check that it is locally compact? That is by definition what we need to do, we need to take any point and any neighborhood containing that point. We need to show that its closure is compact. So what to do? So take any x in x or take any neighborhood v of x. Okay. So by definition, x belongs to, since even is open cover, so x belongs to even for some n. Okay. So x belongs to u1 intersection v and both are open. So u1 intersection v is an open neighborhood of x and its closure is contained in this, and it is known that un closure compact, so closed subset compact is compact. So this implies un v closure is compact. So yeah, so that's why it is sigma compact. Sorry, it is local. So let me repeat this argument for the converse part. X is given to be sigma locally compact We need to show that X is sigma compact and locally compact, right? Let X be the union event. For each event open and event closure compact. So this we get from sigma locally compact, and this thing itself tells that X is sigma compact. Okay. Now, now, um, so now we'll check locally compactness, right? So for that, what we're going to, we're taking arbitrary point from X, and we need to show that we can find the open neighborhood of that point whose closure is compact, right? This is what we need. So what we're doing, we are taking some arbitrary X in X, and we are taking the open neighborhood containing that point. So this implies what? And X belongs to UN for summon. So this implies what? X belongs to UN intersection V. Hmm? Or UN intersection V is an open subset of X. Now UN intersection V closure is a UN closure. Or UN closure is compact. So UN intersection V is whole closure is a compact subspace. Okay. So this is the argument. So that's why it's a locally compact. Okay. So 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 the last one of this was the third assignment. Prove that every locally compact connected topological group G is paramount. So every connected locus, so every locally compact connected topological group is paracontact. So this is what we need to do. Okay. So how to do it? So, I mean, okay, so the solution is quite tricky. So, for that, we are going to use the hint. The following is that if so, first we need to prove that every locally compact topological group is sigma compact. Okay, this is what we will prove first. So, first what we do locally compact connected topological group is sigma compact. First, we will prove this. If we can prove it, then we are almost done. So, now since it's a topological group, so we have the liberty to choose any neighborhood by, I mean, without loss of duality, using the homogeneity of topological group, we can choose a neighborhood around zero and we can choose it to be symmetric. Okay, so let U be open symmetric neighborhood of G whose closure is compact. Okay, now consider the subgroup generated by U. This is nothing but union this thing. I will want to keyboard. Okay, and this is an open. Okay, so it is an open subgroup because it is subgroup generated by something, so it's a subgroup obviously. Along open, so that's an open subgroup. Okay, so it's a proper topological group that opens up the closed subset. The point is that in topological group, subgroup is also closed. So this is a closed group subgroup of G. And since connected, so union even one I equal to 1 to infinity is equal to whole G. Now G is obviously union this thing is nothing but equilibrium. So G is sigma compact and hence Lindelof. Moreover, Lindelof locally compact space is paracompact. Okay. So that's why the full argument goes. So this argument is actually quite tricky. Just hold on. So, so first, by the homogeneous property of Q, we have the liberty to choose any open neighborhood to be the symmetric neighborhood around G. Okay, so U is a symmetric neighborhood G. Okay, this closure component we are taking. So now consider the subgroup divided by U. This is nothing but unit UN. N equal to Y equal to 1. It's open set. Open subgroup also because subgroup generated by U. And in topological group, open subgroup are the closed subgroup. So union UN is also closed. So it is equal to union UN closure. So this tells that G is sigma compact and hence Lindelof. And Lindelof locally compact spaces are paracompact. That's why the whole argument follows. Okay. So this is all about the subject assignment 3. Okay, so let's go with the object assignment 3. Okay. Quite kindly open the object assignment first. Just hold on. Okay. So argument. Okay. So okay, let's start with our objective assignment first. Sure, sure. So the first question is that it's a true false question. So question is that every compact Lindelof space is normal. So, so how to approach this problem? So, so, so basically, this answer is true because you need to use properties of some basic properties, namely locally compact Lindelof is paracompact and regular. So by the theorem then done in the class, it is normal by the theorem. Okay. Compact Lindelof, paracompact and regular. So the next problem is that uh, true false. So we know that image of compact of image and continuous kind of a character. So is it true in the paracompact range? This is the question. Continuous image of paracompact space. Is it true or false? So well, it is not. It does not behave as like a connected compactness. It is unfortunately false. So what is counter? So Uh, Take R with a, I mean, so take any topology X tau, which is a non-paracompact. Okay. And also take XT to be the discrete topological space. Okay. Now consider them ID from XT to X tau. Now since left side is discrete, so it is continuous. So it is continuous. But its image is full X tau, but it is not paracompact. Okay. So that's why continuous image paracompact need not be paracompact. So here we have is one fact this is paracompact, which is quite trivial. Okay. If you have any once again, if you have any doubt, understand why discrete space is paracompact, please ask me in the next session. Okay. So now this question is, let X be sigma compact. Then there is a sequence chain of compact subset X such that X equal to union Kn, and such that if K is any compact subset, then K subset of Kn for some. So let X be compact. Then when you show that there is a sequence K in a compact subset, I mean it's a true or false question actually. So does there is a sequence K in a compact subset so that X equal to union Kn, and such that if X K be any compact subspaces, then is K is the subset of Kn for some. Is it true or false? It's the question. Okay. So well, initially I thought the be quite easy, but later realized this answer is quite very much technical. That's why okay, no. So okay, so it's a very technical solution. So let's uh, get to the detailed solution in detail. Okay. So the answer is false. Well, it is not quite natural. I mean, it is, you can't see it easily. That it has to be false. That's the point. Okay. So the thing is, if it is sigma compact, then it's not necessarily true. But if it is sigma compact along with its first countable, then it is true. Okay, so first we will prove that if the space given X is first countable sigma compact, then it is true. Under some extra assumption, then we will show by giving a counter example that uh, given a statement may not be true if we omit the first countability. Okay, so this gives an intuitive idea of why. I mean, this will introduce why this has to be false. Okay, so let X be first countable sigma compact space. Okay. Also assume sigma is locally compact. One second. Okay. So also sigma is not locally compact. Okay. Sorry, I mean X is not sigma locally compact. Sorry for that. Now, so can be sequence of subsets of X so that X equal to union Kn. Okay, that is we are taking some kind of open power. So each of those is compact. So that each Kn is compact. That is we are covering the X with a compact subset. That's all. Now using this so using this information we shall try to construct a capital K which will not be contained in any of this covered K. Okay. Also we can assume that I mean so it is random open powers, right? K1, K2, K3. So by taking the intersections, if necessary, we can assume K1 subset of K2 subset of K3 dot dot dot. Okay. Now the fact is given that also note the sigma not sigma x not sigma locally compact. Okay, which tells that union of interior Kn which is not equal to x. So take a point P belongs to complement of union of interior Kn. So we will have no neighborhood of P in any of these cases, so it's quite obvious, right? So any neighborhood of P not intersect Kn. Okay. Now choose event to be the fundamental system. That is, it comes from the due to first countability of the X at the point P, such that we can assume the fundamental system to be like this. Okay. Now take P, call P to be P0 and let it belongs to Kn0. Now since U1 does not contain in Kn0, so we may assume P1 belongs to U1 intersection Kn0 complement. So we can take some N1 greater N0 such that E1 belongs to Kn1. Now the same construction repeats itself choose P2 belongs to U2 intersection Kn1 complement. So inductively, choose Nk greater than Nk minus 1 and a point Pk belongs to Uk intersection Knk complement. So this is by inductive process. We are getting doing the inductive process. Okay. Now we are choosing P2 belongs to. Okay, sorry. Now the choice of points are over. Now, in order to construct capital K, put capital K to be all those pk's of the K greater equal to 0. Now, since the pk goes to P, so K is compact. So why? Because any sequence has convergence. But obviously, I mean by construction, K is not contained in any Kn. Okay. So this is the whole argument. So how the argument goes? Let me repeat. So firstly, the answer is false, but there is some strong condition on which the answer has to be false. Okay. So the condition is as follows: the given X is the first countable space, which is sigma compact, but not sigma locally compact. Then under this condition, that if we take any closed sets Kn and any compact sets K, then K will not lie inside Kn for any years. Okay. Now the question is how to do this. So we are taking some subspaces K which are compact, and we are choosing. I mean, so X is covered by some compact subspaces. Okay. Now since I mean we can, by taking the intersection nature, we can assume the K1 subset of K2 subset of K3 dot dot dot. Okay. Moreover, so X is not sigma locally compact. Now, uh, so X is not sigma locally compact, which tells that the union of integer Kn, this union is not equal to this. So we can take some point P which lies outside that interior. So any neighborhood of P not intersects Kn, obviously because all those open, I mean, all those interior UVS is not equal to X, right? Now since it's first countable, we can have the fundamental system around P. Call it even, and we can, without, we can assume that UI contains UI plus 1 dot dot dot. Now choosing P to be P0, that's for writing convenience, and belongs to Kn0. Now since E1 does not contain Kn0, so we can just P1 belongs to U2 intersection Kn0. So then we are choosing N1 greater than N0, so the P1 belongs to K1. And choosing P2 to be K2 U2 intersection Kn1 complement. So inductively, we can choose Nk greater than Nk minus 1 and a point Pk belongs to Uk intersection Kn complement. And this is the inductive process. Now choose capital K to be all those pk's the k greater than 0. Then pk goes to p because the sequential criteria of this the capital compact. But the same construction tells that k can't lie inside k's. Okay, so that's why this. So that's why if x is first countable sigma compact, which is not sigma locally compact, then that statement that given hypothesis is false. Okay. Also, do note one thing. There is some explicit example one construct, but that example goes to some another direction with function analysis. So I don't think it's better to go with that solution. So for timing, should keep in mind that sigma compact or first countable, which is not sigma locally compact, the given hypothesis is false. So, what's it? What's it? So that much is sufficient. Now, wait, let me evaluate. So now what's the next question? It's a true false question. The question is as follows. Let theta alpha be continuous partition of unity on a space X and put theta x to be supreme theta alpha x. Okay. Then this will be the function theta from x to 0, 1, right? Now the question is, theta is continuous. Is it true or false? So hard to solve. I mean, the thing is the way. I mean, the properties which are for the properties for the partition unities actually will give the answer. Okay. So in order to check the continuity, we have another one criteria of continuity. I mean, of course you all know, but let me recall it. If it is continuous, if and only around each point, if we get a neighborhood, so the restricted to its neighborhood, the function is continuous over the neighborhood. Okay, if it is hold for all points and for any neighborhood, then we are done, right? So, well, the answer is true. So, what will you begin? So, choose x belongs to x and choose the open neighborhood you continue such that only such that uh, only finite number of theta alphas on non-zero union. Okay. So, and how will you? I mean, such existence of such is confirmed by the property of the partition unit. Okay. Now, for alpha is equal to alpha one, alpha to alpha. Okay. So, if I find a number to non-zero, let's have alpha one, alpha two. Now, theta restricted to ux is nothing but the max of theta alpha I is equal to 1 to k. Okay. So, it is continuous. So, this implies theta continuous. So, we are showing that, and we have shown that restricted to its neighborhood, the function itself is continuous. Okay. So, this is our one. So, what we have done? We choose some small point x, and so we will get some open neighborhood. So, the only final element is theta alpha and non-zero on u. Okay. So, let's go final limit theta alpha is equal to alpha 1 alpha to alpha. Okay. Then theta u, theta restricted u, and if evaluate that theta restricted u around the point small x, so you'll get it will be max of theta alpha I x I is equal to 1 to k, which is continuous. Because each one is continuous, the max of continuous function is continuous. It's a basic topological property. So theta is continuous. Okay. So that's all it is. So okay. So I think these are the most good problems from the objective assignments. 3. Okay, so let's mm, go with subjective assignment 3. Okay. Objective assignment 3 of the mm, so Okay, one second. What is the assignment? Okay. So just once. So about 2 minutes. Okay. So let's go to assignment 4 or subject assignment first. So the first question is show that anyway we know that sequential compact may not be compact, okay, but the sequential compact which is also T1 space is countable compact. Sequentially T1 compact space is countably compact. So there is a question now how to do it. So countable compact means what you do is if you take any countable over a cover, it would have a finite subcover, right? So let's go using the definition. So let I mean the solution is nothing really difficult. It only uses the definitions of countable compactness and all. Okay, let UN be one countable open cover products. Okay, now if it has no finite, so we are assuming that it is not countable. So that if it has no finite subcover, then xn belongs to x minus union uk k is equal to 1. Note that the set xn is defined. Now, since x is sequentially compact, so the sequence xn converges in capital X to small x. Let's say this small x, okay? And so obviously x belongs to UN for some x. Now since x is t1, so UN contains infinitely many elements of the set xn. But we know that for obvious constant, now for none of the xk, k greater than n are in UN. So who is the contradiction? So this is the argument. So, how the argument goes. So first we took event to be an open cover. So first took event to be a countable open cover for X. Now if it has no finite subcover, then we can choose a small xn belongs to X minus A. Now obviously this is an infinite set. Now the space capital X to be sequentially compact means every infinite set converges of sequence. So without loss we assume that X and that converts subsequent and it converges next to small x. Okay. So X belongs to U1 for Summit. Now X is given to T1 space. So U1 contains infinitely many elements of X. This is the property of T1 space. For T1 space, thus none of the X is bigger than U2. So it's a contradiction. Okay. So that is why the assumption that if it has no finite subcover is wrong. It has to have some finite subcover. So this is the argument. Okay. Okay, so now let's go to the next problem. Let f x to r be continuous variable function where x is countably compact. Show that f is bounded and attains its extrema. Okay. So the first information is given that this function is going to be continuous real value. It is real value function, quite important here, and it is countably compact. Okay. Now we need to show the boundary. So the thing that okay, so in compact, we know in the metric that if the space is compact, then any real world condition is bounded. But if we can weaken this condition by saying that its space is stated, if it is countably compact, then it will be bounded, and it is the extreme. Okay, it's a quite strong result. Okay, so it's quite interesting also. So let's do it. X is given to be countably compact. So the fx is countably compact. Now the thing is if it's countable compact. So question is why? So in order to check this, let un be it's the proof goes same as the proof of the compactness. Okay, I mean the same thing in case of compactness. Okay, let un be a countable open cover of f. Then if inverse of un is a countable open cover objects. Now, X countably compact. So we have so X can be covered by only finitely many if inverse even I is called I is equal to 1 to k. So this implies even I this collection I is equal to 1 to k cover the whole fx. So this shows that fx is countably compact. So what we get? We get some fx which is countably compact that lies in R. And R is the real metric space. So here countably compact and compactness are same. So uh, so it is Heine-Borel theorem. It is closed and bounded. So this tells if is bounded, and since it's closed, it attains its extremum as it is bounded. Sorry, as it is closed. Okay. So first we have done. So the thing is, fx since x is to be real valued function, so fx is subset of R. Okay, and also one more thing is that into the metric space, the countably compact is nothing but compact. Okay. Now, so we'll first try to show f is countably compact. So what we do, we take an even to be an countable open cover for x. So consider if inverse given with a countable open cover of x. Now x is given to a countable compact. So x is equal to finite union of f inverse ux. And so this tells clearly that those finite union covers the whole of it. So fx is countably compact. So and fx contained in R. So in metric space, countable compact compact is 10. So fx is a compact subspace. Okay. So f is a compact subspace. So that's why it's closed or bounded. Since f is bounded, so f is bounded, and since fx is closed, so it attains extrema as it is closed. Okay. So that's why f is bounded and attains its extrema. So these are points. Okay. Okay. So this is the only the first subject for question for the assignment 4. So today is almost 9. So we shall go with the next rest of the question in the next lecture. And in the meanwhile, if you watch this video and if you have any doubts, please ask me in the next live session. Okay. Thank you.